Good morning. Good morning. Thank you. All right, it's great to see everybody. Thanks for getting up early and being here on time. I know there's some people still on the hallway. We're hoping that they hear our voices and make their way in. How's everybody doing? Good? All right. Great. Well, we're day 2 of the summit. We're delighted you're here. So show of hands, how many people learned something new yesterday? Awesome. That is terrific. How many folks met someone new yesterday? Oh my gosh, that is terrific. That is the whole point of Summit. So we are thrilled to see, I think everybody's hands were up for those answers. So thank you, thank you, thank you. And I think you're going to learn a lot more listening to, we have 3 lab experts here today for a panel. We're going to do a couple other things first, but I'm sure that you're going to be able to raise both your hands after today's plenary, which is great. Speaking of today's plenary, please make sure, I think almost everyone has, so apologies for the redundancy, but do download the app. Ahead of today's panel, we're going to be polling the audience so that the folks from the National Labs have a little bit of a sense of the topics on the top of your mind and where you're interested in hearing from them. So please, if you haven't, and Carolyn in her remarks will tell you exactly how to do that. So just make sure that you've downloaded the app for today's panel. And also, because as we've mentioned to you before, but I'm saying it again because it's really important, the app is how we get feedback from you, both on your sessions and the summit overall. So, okay, I'm not up here for long today, so what I get to do right now is to introduce Nate Allen. Nate Allen is a program manager in the Building Technologies office. He is a terrific colleague. I've worked with Nate for many years, and he's going to spend just a little bit of time this morning giving you some updates on some things we've been doing, because we're big believers that we launch things and we start things, and it's really important to keep you posted on where those things we've told you we are going and the things we were doing are going, and a little bit of a look forward for some of the activities we're doing under the Better Buildings Initiative. So speaking of looking forward, many of you know as I exit out of the Department of Energy, Nate's going to be the one to come in and run Better Buildings, and I am so thrilled, and I am looking forward to seeing all the things you guys do together with Nate. So with Nate, please come up on stage and share what we are doing. Thanks.
Good morning, everyone, and thank you, Maria. Thank you. I am excited to be here today to share just some highlights since last year's summit. I'm going to click forward. But first, 2 quick points. So yesterday morning in the public sector meetup, I asked a small group of attendees what key accomplishment of theirs that we would be celebrating next year at the 2026 summit. And the answers that I got back were incredibly specific and well thought out. And it reminded me how impressed I am by your work and how fortunate I feel to get to work with Better Buildings Partners and really the focus that you bring to your work. So thank you for that. Also yesterday morning, in the opening plenary, I heard Carolyn use the phrase barrier busting, which was a new one on me, and I really like it. So, because that's what we do here, and we want to work with you moving forward to help bust more barriers and solve your problems that move our country forward. I'm going to go to the next slide, please. Let's start with a big barrier, here we go, for commercial buildings where HVAC represents 40% of the energy end use, and the technology could exist to help us save a lot of that. I'll begin with an update on the Commercial Building Heat Pump Accelerator, which we launched here last year. This is as a reminder, 3-year effort to work with building owners, operators, and manufacturers to develop and bring to market more advanced, efficient, dual-fuel heat pump rooftop units. The first thing we did after last year's summit was continue working with building owners and manufacturers to finalize a unit specification. If we look at the spec that we are currently working with manufacturers and they're developing products to meet. Based on our analysis for applicable commercial buildings, these new units have the potential to save to cut energy costs by up to 50%. I want to make sure I say this right. The potential to cut energy costs by up to 50% and save commercial buildings over $5 billion annually. This is a significant advancement in building efficiency technology, and it's been an incredible partnership between DOE, the national labs, and these manufacturers. We're so pleased to have 8, and there's some new logos since last year at this time, 8 heat pump manufacturers as part of this accelerator. They are moving way faster than they normally would to meet the demand that Better Buildings partners have shown. I know a couple of them are here. I saw them yesterday. So can we please give them a round of applause? And next, I want to say thank you to all the campaign partners in this accelerator who are supporting this work. These building owners are helping to specify what it is that they want to be able to purchase to help them meet their energy goals. And in many cases, they're also providing roof space very soon to host field demonstrations of these units. Can we please give them a round of applause? So now that I've set the stage on who's involved and what the overall goal is, here's exactly where we are. Right now, all the manufacturers are soon to ship unit prototypes to labs for testing before installing them on some of your rooftops in time for the winter heating season, so next September, October. And when we take a step back and look back on all the activity from this initiative over the past year, I just have to repeat, this is not a normal product development timeline. I really can't say enough good things about how diligently these OEMs are working and how much we appreciate all of your partnership and willingness to support and collaborate in this process. So thank you again. Now let's shift gears. One of the key things we do at DOE is convene. We convene so that you can learn from peers and experts, and also, frankly, so that we can learn from you. These exchanges drive innovation across the marketplace and inform DOE's research and development. Better Buildings partner peer exchanges take multiple forms, such as peer-to-peer calls, design charrettes, and working groups. A year ago, we launched 3 working groups, one on central plants, another on refrigerants, and a third on structured analysis for industrial projects. Each group convened partners, including many of you, and over the course of a few months to discuss these pressing topics, met to outline the barriers that you all are facing. Here's what's significant. Now, reports on the key outcomes from these working groups are now available, as of this week, on the Solutions Center. And templates, primers, and action plans are being worked on based off of the inputs that you all have shared. As we think about what comes next, if you have ideas, and this is going to be a recurring theme, if you have ideas for what you'd like us to cover, please come find us. We want to do what matters to you. And then lastly, I want to talk about some of this great work. We've been working with partners to meet them and meet you all where you are at your facilities through in-plant trainings and energy treasure hunts. In-plant trainings, for anyone who doesn't know, they're 2 to 4 day workshops that are led by Better Plants experts who train participants on how to identify, implement, and replicate energy savings projects. Partners learn about technology fundamentals, receive training on tools, and take away lessons to identify energy savings opportunities and best practices to implement at their own facilities. As a show of hands, who here has participated in an in-plant training? It's kind of dark in the room, but I'm seeing hands go up, so that's good, yes. Okay. Since 2011, Better Plants has organized over 200 in-plant trainings, engaging more than 2,800 participants. These trainings have collectively identified more than $50 million in potential energy savings and assisted partners in overcoming key barriers to implementing energy management practices and technologies. I'll share that I've long been impressed with how the industrial team facilitates these in-plant trainings, and I've been really encouraged by some recent planning to see if and how we can replicate something similar, probably on a technology-specific basis for our commercial partners. Stay tuned on that. I want to draw attention to our energy treasure hunts. Last year alone, we had 17 energy treasure hunts, identifying more than 350 energy and water recommendations. Each event yielded an average of 21 opportunities and achieved approximately 19% in total energy savings. You can see we have a robust schedule throughout the year with partners that include Owens Corning, Frito-Lay, JSW Steel USA, more. These commence in a few weeks, and we're already excited for the outcomes that we know they'll yield. And again, looking forward to the year ahead. If you have ideas for what we should focus on, please let us know. You can provide feedback through the Summit app or talk to one of your program contacts here at Summit. We do take this feedback very seriously, and I hope that message is coming through in the sessions as well. It's really significant for us, for our annual planning, to hear your ideas and what matters, because that's what drives this program throughout the year. And that concludes with what I want to close with. So I want to thank you all for being here and for collectively pushing forward. And I'm thinking back to that question that I was discussing with some of our local government leaders yesterday. What is it you're going to achieve over the next year? How can we help you? I want you all to come back so that we can celebrate that success and whatever barriers we busted through together. Before I fully wrap up, she's shaking her head no at me. Yes. I would be remiss if I didn't acknowledge Maria, who has been a colleague and mentor of mine for some years now. I know Maria well enough to know that she does not want any fanfare right now. In fact, last night I walked to Metro with her and I said, Maria, I want to talk about you tomorrow, and she said no. She wants me to pass the microphone to Carolyn so that we can get on with this lab panel, yes. But I'm not going to do that because, Maria, I want you to know how much I respect what you have built and how you have built this program into what it is, and that it's a great honor for me to help steward it forward. So thank you. And as the slide says, we would love, the slide did say, join us next year. We'd love to have you come back. You could be a moderator. Something tells me you won't be here. Let's give her a round of applause, please. The least we can do, Maria. With that, I'd like to invite to the stage our Deputy Assistant Secretary, Dr. Carolyn Snyder, who is going to moderate our lab panel. You know Carolyn at this point. What I'll add that you won't read in her bio is that she is revered among her staff for her intelligence and the thoughtfulness that she brings to her work. And I know that she is a tireless advocate for this partnership program, and I think we should all be grateful for that. So Carolyn, I pass to you.
Thanks, Nate. And as all of you know Maria well, she would never even think about retiring if she didn't have complete and utter confidence in Nate and our whole team and all of you that you'll keep doing more and more every year. So thank you so much for that kind introduction. So I'm really excited about today's panel. This is our Stump a National Expert type of panel where you get to ask any question that's on your mind. We've got leading thinkers across our country here with us today. So I hope all of you know what a DOE National Lab is, or at least have seen Oppenheimer. If not, they are just as cool and exciting today as they were many decades ago. I really think of our national labs as a public service brain trust. We have public servants who are fully focused on being world-leading scientists, but on problems that mean the most to our country. And that is a really special combination. Our estimates are the return on investments are over 30-fold from public dollars invested in new technology innovation in our national labs. So with that, I'm gonna welcome to the stage 3 leaders from across our national labs. Come on up. We have Mary Ann Piet, who is the Associate Lab Director of the Energy Technologies area in Lawrence Berkeley National Laboratory. We have Judd Vierden, who is the Associate Lab Director for the Energy and Environment Directorate at Pacific Northwest National Laboratory, and Robert Wagner, who is the Lab Director of the Energy Science and Technology Directorate at Oak Ridge National Lab. And a lot of longer names. Really, these are the top leaders in each of these massive, important labs who work on the space that we all work with. Those experts that you work closely with across our program are from their teams, as well as the National Renewable Energy Laboratory, our 4th major lab partner in this program. So thanks for joining me up here. Here's how the program's gonna work today. We are going to have two main sections of our panel today. The first is I'm going to turn to each of our panelists. They're going to briefly give an introduction to who they are and the work they do, and then give you a quick sense of 2 to 3 innovations that they're really excited about right now. And then we're going to do Q&A, and that's really open Q&A from all of you. The first time I got to lead this panel, we had people running around the room with index cards governing everyone's Q&A. We are in the modern era now of our apps. So, unlike normally, please take out your phones. Everyone, right now, you got to take out your phones. Okay, open up the app. You should have the app by now, yes? If you don't have the app, you're going to miss out on fun today. Okay, now, if you don't know how to do this already, open the schedule part of the apps, find our plenary, which of course you've already loved with lots of hearts and whatever other ways to like it in the app. And there will be 2 buttons when you look at our plenary in your app. The first is there's one that will be titled Polls right under the title. There's another button that's Q&A. So to make sure you all have your phones out and to make sure that we're focused on our audience, because we heard that in the communication conversations this summit and in the lessons learned, know your audience. So we want to get to know you even better. Go to the polls button. You're going to come back and go to that Q&A button throughout the panel, because that's how we're going to be driving the panel today with questions. So open up the polls, and we will start our polls today. Our first to hear from all of you is, what is the biggest challenge your organization faces in adopting emerging technologies and practices? So we see some really great themes here: uncertainty around return on investment, high upfront costs, so a lot of questions around how we can be addressing the cost of many investments, the lack of technical expertise. Oh, can we go back to the slide? Thank you. But also elements around access to data and regulatory and policy barriers. So things to keep in mind, panelists, as we go. Okay, our next question. What emerging trend or technology do you think will have the greatest impact in the next 5 to 10 years? We're going to hear from our 3 national experts on that question in a few minutes, but love to hear from the group. AI and machine learning, electrification technologies, great. These are already ones that we've already been talking about in our lead up. Smart building and IoT. Distributed energy systems, advanced building materials. Okay, lots of great topics that we'll be coming back to. Also great ones that I know we've had throughout this summit these last 2 days. Thank you all. Panelists, you're paying attention. I love this. Looking at, you know what you're going to have to talk to. Okay, last question. How familiar are you with the latest advances in built environment technologies? Safe space, answer honestly. I love it. We got a real mix across the room, which is Summit at its best. A lot of people who've been here many years, a lot of people, it's their first Summit. People from all sorts of backgrounds. We were talking the other day, I was in the hallway with someone yesterday who was trying to decide were they going to go into a deep dive into heat pumps for industrial systems or a communications workshop. And that to me is just like, that's the Summit. I don't know, which one am I going to go to? Maybe I'll go to both. Okay, thank you all so much. So with that, we are going to start with each of our panelists, and they've wonderfully sat in order for me so that I obeyed my instructions. Thank you. So Judd, please give your brief introduction and some of your thoughts on emerging innovations.
Well, welcome everybody. I am so excited to be here again. It's been a couple of years. I'm Judd Verdon from Pacific Northwest National Lab. You can Google me to find out, what I do and all that type of stuff. But I have the best job in the world. I've been at Pacific Northwest National Lab 33 years now. I lead 1,700 scientists, engineers, professional staff who do everything from nuclear energy to environmental cleanup to next generation batteries to grid resiliency and reliability. We work with utilities all over the country looking at cybersecurity for the U.S. Critical energy infrastructure, biomass conversion, sustainable aviation fuels, you name it. I get to work with all the most interesting people and all of you from industry and all these things. The biggest part of our portfolio is the Building Technology Office. And the Building Technology Office is some of the things I'm going to talk about here. One last thing that you've all experienced that has come out of P&L that's maybe touched your daily lives is when you go to the airport and you do this. That came from us. So you're welcome, for that. But what's kind of cool about that story, just really quickly, that from 25, 30 years ago came out of an Army program to look at stealth fighters and use millimeter wave sensor technology to see if it still had its stealth signature. And then after 9/11, it got swung and adapted completely for airports. So as Carolyn said, you never know what's going to come out of research for years and years and years, and it's part of our job to pull it out and make it impact the world. So I'm going to talk about buildings, and I'm going to talk about some of the things that were in the poll. This is a thermal energy storage unit outside one of our buildings. That's Srinivas Katapamula. He's our lead engineer. Everyone knows Srinivas? I just assume the entire world. It's all the people from P&L. He is one of the experts in this space, and let me get you connected with him if you have any detailed questions. If we can go to the next slide. This I wanted to show everybody because it's, I think, what I spend most of my time thinking about now. And this is the rapid adoption of new technology. And it's going from the 1900s to 2010. It's actually been updated between 2010 and 2020. But if you look at the curves, everything on the left-hand side, you can just see it visually. Telephones, electricity, cars, radio on the left-hand side took decades for us to build the infrastructure. And now I think you all must feel it. You can see it on the right-hand things. Things are happening so quickly to us right now. All the new technology that's hitting us, everything from hyperscalers, and they used to say oil is king. The report that goes along with this says data is the new king. If you look at wealth, it's all about who has data and who controls the data. If you go to the bottom of that, where we're at 2010, it's tablets and smartphones and social media and HD TV. Then there's things on there like Blockbuster or VCRs that would have gone up and completely disappeared in that same time frame. So all of us in the national lab system and universities and industry, we're faced with this rapid change of everything coming at us. Everything from bigger scale, but also everything is being focused back down on things like that are becoming cheaper and smaller and more powerful. So interconnected devices and wireless devices, everything being connected to data. I think it addresses some of the questions that came up there. Low-cost computing power. My goodness, those of you who are Googling me on your phone right now, you can see, look what we hold in our hand. That was more power than a car had 30 years ago. I mean, the world and the rate of change is just incredible. And then it was also in one of the polls, data analytics. The ability to pull in data and process it to make things smarter and more efficient and more effective. It is just changing both on the big scale when you hear about data centers, but also in every single thing we do in our life. And so the thing I wanted to talk about is some of the work we've been doing, really to look at how we put all those pieces together for our campus. And this is a site of us out, I'm in eastern Washington. We're actually out in the desert, 7 inches of rain a year. That's the Columbia River. We were there because when we did the Manhattan Project, that's where our country chose to build the nuclear reactors. It was out in the middle of nowhere where there was plenty of water. And our lab grew out of that nuclear production site. So our campus, we have about 6,400 people at our lab. We've been working really hard, and by the way, we're becoming transmission constrained. We're becoming energy constrained. So we'll be 500 kilowatts short of peak power in about 2.5 years if we don't do something. So we started to look at our campus and try to understand what we can do to save energy in our buildings, because it's really going to matter to us. So we took 4 buildings, and we put some automated controls into it, and these were first commercial control systems. We demonstrated that you could have 20 to 25% savings, and that was just looking at set points and scheduling and holidays and managing those building controls, something pretty basic and simple. But like one of the questions earlier from your poll, it's too expensive, for us to implement. So we started to look at how could we develop low-cost supervisory control systems. And that device, that Voltron device, is just a little Raspberry Pi that you can put all kinds of control and power, computational horsepower in. We started to deploy that across our 4 different buildings. We were able to show with kind of open data systems how we could do it in a cost-effective manner and maybe scalable across our campus. The payback, we think, and this is, I think, one of the most important things, could be less than 3 years. even if you're at 10 cents a kilowatt hour. Part of our challenge up where we live is we're at 6 or 7 cents a kilowatt hour, so electricity is cheap, so we have to find really good options if we're going to reduce energy in our buildings. By the way, on that work on the left-hand side, we're now deploying it as of a year ago in 2 facilities, 2 buildings in Texas. We've demonstrated 10 and 20% energy savings for those 2 facilities, and we've also built in rooftop control units. This device, this low-cost supervisory device, can also integrate batteries, thermal energy storage, electric vehicles, connected lighting, so it can link everything in a building and try to reduce the energy. And then behind that, one of our buildings on the right-hand side is about a 120 kilowatt, 250 kilowatt hour battery. It's a lithium-ion battery system. And behind the building on the right is that thermal energy storage system that I showed, about 80 tons. We've integrated that with our building, and then we started, because we have demand charges and where the time of day pricing is really important for us, started to demonstrate where we can use that battery with only a 40% depth of discharge and save 10 to 30% in capacity. So from a campus management point of view, we're trying to put all these different pieces together to show how we, in a low-cost way, where electricity is cheap, where we can use open source hardware and software, we can integrate and put these pieces together. These combined things that I'm showing on this slide, we're going to go up to Spokane and Salt Lake City and deploy them in another 25 to 30 buildings in the next year and look at the benefits of an integrated system that's low cost, maybe even automated when you deploy it so you can reduce labor costs. So with that, I will hand it over to Mary Ann.
Great.
Wonderful. Thanks, Judd.
It was wonderful, Judd. I learned a lot about your campus, and I really appreciate the view. And I'll try to take some of those themes and go a little bit further with them. I want to start by saying thank you to Maria and thank you to Carolyn. It is wonderful to be here today, and this is a great event because it's an event where the labs and the industry, commercial buildings industry and the manufacturing get to interact, and it is such a pleasure to be here today. I heard yesterday morning's plenary, which I thought was wonderful, and I'm looking forward to sharing with you a little about what we're doing at Lawrence Berkeley National Lab. You heard from Carolyn a little about, if you've seen Oppenheimer, you've seen a little about Ernest Lawrence and Oppenheimer that helped develop particle accelerators. So we started in 1931 doing that kind of work. The Manhattan Project was in 41. So we were moving from the UC Berkeley campus up to the lab. I also moved from the UC Berkeley campus up to the lab when I took a class from a physicist named Art Rosenfeld, who also was Enrico Fermi's last grad student. So we have this long history in physics, but we care about all kinds of challenges to the US economy. And during the oil embargo, we pivoted from high energy physics to energy efficiency. And we're in a very similar time today when we look at what's happening with our energy systems. Typically, electricity use has been about 1% low growth in the last few years, but now it will be 15% over the next 5 years. So energy efficiency is as important as ever. And in the energy technologies area that I oversee, it's not quite as broad as what you heard from Judd, but we work on energy storage, hydrogen, building energy efficiency, and industrial technologies, and I'll give you an introduction to some of those things I'm excited about. On the left, that thin triple window is a super exciting window that was patented many decades ago, but we can actually build it now because we can build that thin piece of glass similar to the glass on your iPhone or your TV. And similar to Judd, our story is the National Fenestration Rating Council was developed at LBL, and every window you have has a little NFRC rating on it. So we helped develop the science of how you rate the performance of windows. That window, our team gave a talk here a few years ago to find a partner site. And that building, that window is being tested in Dane County, Wisconsin, thanks to the Better Buildings collaboration. And they tested it, and they made sure that people were more comfortable as well as saving energy. So that window fits in the footprint of a double pane window, but it doubles the R value from a double pane window to a triple pane window. So we're really excited to partner with you to test things like that. Wisconsin is one of the places we're also testing energy information systems and fault diagnostics. And the picture in the middle is in Madison, Wisconsin.
So we care not just about the thermal performance of the window. It turns out that about 1/3 of your HVAC losses are actually lost through the window because the facades are often leaky. Similarly, your HVAC systems, as Judd sort of alluded to also, have dampers that are stuck and sensors that are out of calibration. So we're working on control systems that can take that data, and you heard at yesterday's plenary about digitizing the information. So we want to turn that into actionable information that facility managers can use to reduce the energy use. We can typically save about 10% with better information systems, and as we move into fault diagnostics, we can actually automatically find those things instead of having all the labor where the HVAC people have to run around and figure out where, I see a fault, now which sensor was it that caused that fault? So huge opportunities there. We are creating those things with AI now. So we're really moving into this era where we want to take machine learning to understand the seasonal changes in the building and build digital twins to facilitate energy efficiency. And on the right, similar to the campus at P&L, we're trying to deploy these things at scale. One of the things that's happening with the electric grid is that we are seriously need to understand whether we have reliability issues when data centers might drop offline, or with all this load growth, how are we going to protect the ratepayer from the high increase in building out the grid? So we care a lot about making sure that you have affordable bills, and one of the ways we do that is with demand response. So with demand response and demand flexibility, you can actually reduce your bill by helping the utility flex their load and manage the grid if there's a frequency or a voltage dip, or some sort of peak event where the facility's really struggling and the grid is helping to communicate with facilities in an automated way. So at the Connected Communities program, we have 10 facilities around the United States where we're going from not just individual building retrofits to community scale retrofits. And the Ohio State campus, The Ohio State, is one of our sites where they're saving about $200,000 a year just on demand charges and another $100,000 a year on utility programs and demand flexibility. They're using thermal storage, controls, and I have an acronym that I wrote down that I wanted to share with you because they also have one of their scientists who's really good at acronyms. And they have something called the Automated Building Control with Knowledge of Distributed Energy Resources and Electrical Systems. And if you really are careful, that says Buckeyes Go. We also work with you on what's called the Industrial Technology Validation Program. And a lot of these partners are here in the room or here this week. I am so excited to share with you some of the things we do in that program. For both of the auto manufacturers there, we worked on some of the cooling tower technologies. In those cooling tower technology demonstrations, we actually were able to reduce the water use by 10% and chemical use. So they could save 30% of their chemical use. Now, it's really important when we think about industrials and manufacturing, they care about the energy use, but they also care about water, chemicals, and other process loads. So we work to help you guys define what are your needs. One of the key things that National Labs do is try to understand your challenges, try to develop solutions, and try to validate the performance of those technologies in the field. So the Industrial Technology Validation Program is one where we hear from you what your needs are, we form a project, we go into the field, and we create verified savings that we can scale to other partners. And on the middle one, the Alstrom-Mundsku, that one is a membrane system, black liquor concentration. And in that site, we're actually concentrating the membrane, the black liquor, using this membrane, so they actually have much less steam energy use in that facility and great savings for that black liquor concentration. That's a paper mill in Wisconsin. And on the right, it's a steel manufacturer. In this case, we're looking at electrochemical water treatment and electrocoagulation oil removal. That site is actually taking oil out of wastewater, and they actually were able to reduce the truckloads that take the waste products away. So these are kind of holistic systems that we're helping you evaluate in the field. And my last slide is something you've been talking about at the event this week, and it's around data center energy use. In December, we created the report to Congress. The picture on the left has been on the cover of the New York Times. And we know that this is a big challenge for all of us. I want you to think about the energy for data centers, the energy for AI, as well as AI for energy. And that was one of the things you noticed as one of your priorities. So we want to support the hyperscalers building these things out, but we also want to make sure that you all are having access to that technology and the kinds of things that you're doing. The data center energy has been about 4% of US electricity use, and that could triple up to 12% by 2028. We're testing all the shipments of all the servers, the GPUs and the CPUs, and on the right there's a picture of the map of the United States, 3,500 data centers, so we're tracking all the data centers, but we're also tracking where they are on the grid. So when you think about those data centers, think about that waste heat utilization and whether there's something you might do. We're actually looking at things like Stirling engines, we're looking at advanced cooling technologies, and load flexibility. So we know that those folks can get connected to the grid faster if they have demand flexibility. So I want to really thank you all today for joining this event. Again, thanks for allowing me to participate, and I look forward to the discussion.
That was wonderful.
All right, thank you for having me. Those were great lead-ins. In fact, Judd, I've been to PNNL and I've toured some of that, and what you were talking about. It's just amazing.
This?
Well, so I'll add to that. So, no, I don't enjoy that. Yeah. So when they stop you and they want extra screening and they wipe your hands and your luggage, so there's Ornell technology in that too. So Judd and I both really mess up your trip. Anyway, it's wonderful to be here. This is a great lineup for discussion because all three of us come from Office of Science labs. And really what that means is we steward big science facilities for the Department of Energy. And missing is our good friend, John Farrell from NREL, who we work a lot with, and he is, that's the lab for energy efficiency, renewable energy. And so think of that as the Applied Energy Lab, and it's just been a great partnership. We all bring something to it. I've really enjoyed it over my career. So I steward energy science and technology at Oak Ridge, and that's buildings, of course, manufacturing, grid, and transportation. So we have big facilities in all those areas. And then our Office of Science facilities are around computing, neutrons, materials, and those are kind of the things I think are special we bring to this discussion. The other thing I'll point out too is we also work very much across all those applied energy areas I talked about. And I think you're going to see that a bit because I have a kind of a manufacturing bend to what I'll talk about today. So a couple things I wanted to focus in on, and I think this is great. You guys have really talked about systems and how you bring all this together, and this is more of maybe hardware that we're trying to deploy. And this first example, actually both examples I'll have on this slide are based on a technology called Big Area Additive Manufacturing, BAM. How's that for an acronym? And it was developed about 10 years ago, and think about printing polymer carbon fiber mixes on large scale. And so that was a technology we developed with industry. It since has become an industry in its own, and the applications we have now are more trying to work with industry and how to do special things related to it, but it's not something we do fundamental work on anymore. But this case is a case where the Domino Sugar building was putting a new facade on, and they were making all these molds for concrete out of plywood and fiberglass, and it's very time consuming. We worked with this company called Gate Precast, and we were able to print the molds, which is very fast. They're more durable, and we could very customize the shapes. And it ended up to, and their estimate was it decreased the mold production time by over 2,000 hours. So it's pretty simple technology, but it's out there now. It wasn't simple when you developed it, but it's out there now. It's accessible, and it's helping make a difference in saving time and money. The other example is, and this is not being deployed yet, this was done with the University of Maine, is you build these big commercial buildings and you have these cassettes in the floor that handle all the infrastructure of the building. They're pretty complicated. There's, let me look at my statistics, 39 parts, lots of screws, different materials, very cumbersome to put together. And so at the University of Maine, they're looking at a polymer mix and looking at how do you print these where they're very quick, they're single piece, they have the strength that you need, and it's an easy replacement. So there's just two examples. If you've ever been to the Forrestal building, which a lot of the DOE folks hope have been in the Fort South building. In the lobby,
About
there's
as much fun as.
not similar. There's a Cobra vehicle in the parking lot, or not in the parking lot, in the lobby. And we printed that a decade ago. And it wasn't to say we're going to print cars, but it was to say, look, you can print really big things. And it really accelerates how you do things. The second example I had was really around AI and automation. And from a building retrofit and building construction standpoint, and on the left, I'm showing where we've come up with different algorithms to really accelerate. Say you have an existing building, you want to do retrofit to it, you need a digital twin. You can very quickly do a point cloud, use AI automation, and you can come up with a digital twin very quickly. We've also done cases of this where we put it on the supercomputers, and then you can do it, of course, very fast. But the intent is that people will be able to do this in the field and do it fast. And you can use this with other technologies that have been developed. This one's called the Real-Time Evaluator, which had an R&D 100 award, I think it was last year. And you can use these digital twins with this real-time evaluator. In a couple ways you can do this. You can work with crews that helps really accelerate how they place different panels, or you can do it for retrofits. With retrofits, one thing that makes me very excited is go look at any building or house or anything you want to retrofit. Heck, go home tonight and stick a square in the corner of your room. Nothing's square, nothing's the same. And it gives you a real digital twin very quick, and then you can go and you can start building retrofits that are going to fit exactly what you need. And then on the bottom, there's an example where they're heading with this, and I've seen this done in the lab, is how do we enable this where it's fully automated, and so now you have machines doing 24/7, putting up buildings or setting up retrofits. So a lot of really interesting technologies. AI has been mentioned several times, and I'll jump to the punchline. I think over the next decade, that's what's really going to drive a lot of change. And then I have one final slide, and this is more of a thinking forward. And I have to credit Kashif Nawaz. He's really inspired a lot of discussions with me on this. Computing is amazing. It's going to continue to get faster. AI has grown at a rate I couldn't have imagined. I remember 2 years ago when ChatGPT came out, looking at it with my daughter and just couldn't believe what I was seeing. And now look where it is 2 years later. It's in everything we do. Materials are moving fast, and a lot of this is due to computational power and different new types of characterization methods. And then on top of that, manufacturing. So you put all this together, and you can start looking to what's happening in nature. And actually, it's no longer saying, wow, that's interesting how nature did that. How would I ever build that? How would I ever make that? Now we know how to do that. And so that's somewhere we're leaning in hard. A couple areas where I'm really excited is passive ventilation. And there's papers out there on this. You look at papers on termite mounds and how they're able to have lower temperatures inside, very complex structures, drives natural convection, keeps it cool, keeps it stable. Challenge has been, how would you optimize that? How would you make that? And now we have the tools to do these things. So these are things we're leaning into. In the middle, there's a lot of examples in nature about very, very durable structures or shells. The bottom one I think is interesting with windows, because think about new films that keep the infrared out, let the light, the visible light go through. Huge potentials there as well, and that's a big manufacturing opportunity. And then on the materials side, we're all familiar with things like, I think, with spider silk and the structure of bone, and again, things that can really inspire you, but how do you do it? And I think we're well on our way there. And the last one is self-healing polymer coating. So imagine a coating that has various additives in there, where if there's a puncture or other issue, those additives are released and able to heal it. There was a recent example from Oak Ridge that was just recently licensed to a company called Flexcon. That is a film that basically, if it's punctured, it self-heals, and that's more around sort of a memory of the film and of the material, but same kind of idea. And with that, I will stop. So thank you for your time. I hope it's going to be a lot of fun.
So now you all can feel why it's so fun that I get to work with such amazing scientists across our national labs. So we are going to question time now. So if you didn't put some questions in the Q&A part of the app, please run in to the app and start adding questions. But we've already got a bunch, and people are voting for their favorite questions. I'm going to start based on the poll. One of the big elements that was called out was cost challenges, both uncertainty around ROI, challenges with upfront costs. What are the national labs doing to help people in that? How do you think about that?
So I can help jump in on that. So, there's a lot of parts to cost. There's that first sort of, how do you get over the hump and even explore some idea you have and do it in a cost-effective way. And I'm sure other labs have similar approaches, but one of the approaches we have is we have it's called tech collaboration programs. We have these in buildings, we have them in manufacturing, where for really a fairly small investment on both sides, no money goes between, everybody can come to the table, try out something, see if there's opportunity and interest in going further. And if so, then there's other mechanisms to everybody brings money to the table and figures out how to move as a team. But then the other important part of that is opportunity for kind of a low cost, de-risk and try to understand if there is a future, but also by working hand in hand with industry who has to sell a product and get it out there. From day one, we're thinking about the affordability of it. And, we're not thinking about if it's going to be subsidized or any of those things. It's like when it hits the market, is somebody going to be able to buy it? So.
There are a variety of things that influence costs. There's the hardware, the software, and then the soft costs or the labor cost. It's very important in building technologies to try to look at things like panelized construction, where we actually were testing at FlexLab recently a window that was already built into the wall, because windows are expensive to install, to retrofit. So we're looking at panelized construction to help reduce costs. We're also looking at training and AI, again, to understand when somebody comes to retrofit a heat pump in a building, what are the things they need to do, kind of like your digital twins. So we need to keep helping to collect the data of what are the costs, what comprises the cost, and then how can we work on each of those components to make reductions.
Yeah, and the only thing I would add, and one of the examples I tried to use is on the building automations and control. There's like 5.9 million commercial buildings. The vast majority of them don't have any building automations and control. I was asked one time, with all the technology, why aren't we deploying everything in buildings? And I said it's very hard sometimes to get an ROI building by building. And there's huge benefits, whether it's, some of the things Marianne mentioned, if you're trying to do demand response or, offset transmission builds or offset substation upgrades, but our business models don't aggregate at a level to fully recover all the benefits from every building. So if the policy doesn't change, then what we have to do is drive the technologies to be low cost, interoperable, and you said the exact same, the most important part is the labor costs can sometimes be the things that keep you from scaling it, deploying it. So we're working really hard to make everything automated, interoperable, go into a building, it connects up to wherever you have a thermostat or rooftop unit or battery or management system, and then very easily and quickly can optimize for whatever you're trying to optimize, whether it's time of day pricing or overall energy use. It's going to keep coming, but the scalability problem, I think, and the policy problems is still a challenge. We need to be able to aggregate the benefits in a lot of these cases.
Thank you for that. And Robert, you touched on this a bit, but there's a question in the Q&A. How do you help make sure those technologies are successful and get commercialized and judge that steep curve of the speed of accelerated adoption? What are the labs doing? You don't just start doing some R&D and just cross your fingers and hope it succeeds later.
I guess I'll go back and emphasize this working hand in hand with industry, and often multiple industries. And an example in the manufacturing side, and it's applicable to buildings, is right now we're doing things in how do you improve domestic security through being able to make big metal parts. Really, I'm talking 100,000 pound kind of parts. And we're working with a lot of different industries and finding there's a lot of pull to this. And you got to have that pull and a real need. It can't be, boy, that's cool, I love the science of it. That's not going to get us where we need to be. And so I think just making sure you have enough people lined up who are interested, that's the potential to, in this case, I'm thinking of nuclear, you could revolutionize an industry if you're successful. DOE helps us take those risks a bit with industry. So it's maybe not a super satisfying answer, but that's how I think about it, making sure people are together and they see an end to it. And then you hand off. You don't research hobby it. You get to a point and you step away and you're there to help. You move to the next thing.
Yeah, I want to say I met somebody here, maybe they're in the room still, from Wendy's, and they're part of the small building controls program to try to accelerate the use of controls in small buildings, because large buildings have more sophisticated facility managers, but you mentioned small buildings also, and there's so much education for the people in the franchises to understand the opportunities for better energy management, to actually communicate with them about the opportunities with small building controls, to understand how they can reduce their electric bills, or gas bills, their energy bills, and share that. So these learning cohorts, like the Better Buildings program and the Better Plants program have here, are such an important piece of getting things done and scaling.
You know, and the one thing I've observed and learned over my time at DOE is we are at our best, I think, in the applied energy space, when we really understand your targets and your goals. Because we don't live in the market like you all do, and the market drives so much of this. But when you can help us distill down, here's our market challenges, and give us performance and cost metrics that we can then evaluate our progress against, it really helps us be much more efficient and effective and focus on the right research.
That's great. So speaking of grounding in real world problems, one of the questions points out that 2 years ago, a major point of discussion was around long duration storage and transmission. And I'll add that those kind of conversations around grid integration and upcoming electrical infrastructure costs have continued. And I know the data center conversation has only accelerated that. Any latest insights or updates in the grid integration, long duration storage, transmission space?
Yeah, I think we were part of with the National Renewable Energy Lab, a national transmission plan that started to look at what transmission's on the books, what's planned, and where's the gap that's going to leave us. And at that point in time, that was started 4 or 5 years ago, it didn't include all the hyperscalers and those types of things. But it's still progressing. And the next step on the transmission planning is, this is a big national plan. We and other labs are focused on what's the regional plan. Because energy is regional, and so we're going to have to get down to regional plans for transmission and work with utilities. The long duration work still continues. The long duration numbers, people were talking about 12 hours plus. Everything's on the table now, everything from natural gas to fill that gap to pumped hydro. So there's a lot of ideas still being put on the table. From the battery side, we just opened up a new facility. It's called the Grid Storage Launchpad. And it's designed to go everywhere from the full spectrum, from fundamental materials to 100 kilowatt testing. So when we talked to utilities, they said, we won't believe a battery system is real until we see it at 100 kilowatt tested under realistic grid conditions. So we built kind of that whole pipeline. And then the major focus right now is to find those new long duration materials that have a strong US supply chain. Because almost on the battery world, on lithium ion, we're highly dependent on nickel and manganese and cobalt from other parts of the world. So it continues.
I have a quick comment. Yeah, I have a researcher at Lawrence Berkeley National Lab who retired, and he became a member of the CAISO board, the grid operator in California. And we recently had him over on a brainstorming session on what are some of the challenges in for the grid operators. And he made a remarkable comment to us that, the duck curve problem has actually been solved because we have, over 10 gigawatts of storage right now. And I don't think we still have overgeneration on spring days, but there's a lot of storage that is getting installed on the grid. So, this is a kind of you invest in the grid, and then the things change, and it's evolving, and there's a lot of changes regionally. But, there's also better information with synchrophasers and grid operators to better understand the health of the grid. And there's a lot of investment in communications technology, both at this macro scale as well as the local distribution system. So a lot to do still, but a lot of progress as well.
A couple cool advances in that space. So California's been great with the 10 gigawatts, and it manages that big duck curve, balancing out all the solar. But on meeting kind of peak load, we and others are looking at, if you could take the existing transmission infrastructure, and with synchrophasers and others, you can understand the real power flow in real time across big transmission lines. It's like a speed limit on a freeway. You can only put so many electrons through it. If you watch it in real time and you can control it, you can put more electrons through, so you're going to get more transmission capacity on the existing line.
Yeah.
And then some really cool work on new transmission lines that have higher conductivity. So you can reconductor a lot of the existing stuff. You don't have to build new transmission lines, reconductor it, and move more power through it.
Robert, bring us to the east.
So there's not much I could add to that. I mean, that was great. The one, especially with the flexibility of the grid now too, with basically dynamic microgrids, and there's so much we can do. But the one thing I'll add that I think about a lot from a transportation perspective, but there's other perspectives to it, is I'll say shorter duration storage too. It's massive. You know, if we have a future where we're going to electrify, say, commercial vehicles, and you're going to jump one to plug in a megawatt. You know, there's storage technologies that maybe only hold for an hour or two. It's kind of like filling a tank. It's a capacitor, and then you can pull off without hurting the grid. So it kind of buffers the grid. So that's the only additional thing I would add that I think about, is a little bit shorter duration storage.
That's great, thanks. So we talked about you each mentioned elements of this. We've got questions about it around AI and data and how that's changing things for all of us. Normally I'd say, okay, 5 years from now, but looking at Judd's chart and how fast everything's moving, 2 or 3 years from now, how are things going to be so different from the partners in this room because of AI and data? What are some of your projections or really exciting developments you'd want to share in addition to what you've shared already?
Well, you know, I just do think that from a speed point of view, it is going to be AI and data. And so our lab directors just did a thing called an AI Jam, and it was pretty cool because they got the access to the latest hyperscale platforms, all different kinds of platforms. And you know, I sometimes think, oh, I know what's going on the cutting edge, and then I see the questions they ask these hyperscalers. These are like the big data centers, high energy, and they're expensive. They might cost you like $1,000 a query. But they were asking them really complex problems about the energy system in some cases, and they were coming back with good answers. And so I just think, you know, the amount of information in 5 or 10 years from now that we're going to be able to feed into the computers, and the amount of useful information coming back is going to change everything that we do. You know, and I think that the biggest advice my boss came back to me and said, and I'm listening to it, was, and I've already done it, is go start playing with all these Gemini and all the other hyperscaler tools, because they're going to transform things. And so it goes back to my earlier comment, data is going to become king. You know, whether it's in a building or a community or a campus, we can measure everything, we'll be able to pull it in, it'll be interconnected, and some smart person is going to figure out how to do it faster, better, and cheaper, really quick.
I'm super excited about AI, and I agree with Judd that what we're seeing in chemistry and in materials is remarkable. One of our challenges in buildings is getting the data out of the building, and a lot of us are spending time on interoperability and naming conventions, so there's a lot of work that DOE's funding and working with partners. I think the folks in the room also know there's going to be a lot of startups that are marketing AI technologies to them. So there's going to need to be a lot of sharing amongst yourselves around how did it go with that startup? How much did it cost to host that tool? Because they're going to take your supply air temperature and your electric use and the weather data and your occupancy data and make sense of it. And that's really great. And so there's going to be a lot of new tools, but we're going to need to actually understand the business models around those and how to get the data out of your control systems and your facility to feed into those things.
Then I'll just add to that, and it's been talked about a bit, is all these data centers. You know, what does that look like? And they're coming fast. And right now, I think the approach is more, just build more, and you know, they'll be as efficient as they'll be efficient. But there's, I think, a lot of fundamental work to be done on power electronics for them, on the processors. We have a lot of focus on heat transfer, thermal management, immersive cooling. You know, how do you every bit of energy efficiency you get is energy addition to the grid, from my perspective. So how do we really do this? I mean, we talk about it, but I don't think we're there, have a good plan. So a few years from now, I'm thinking we're going to be a lot further along and a lot more data centers.
So speaking about the future, we've got a few questions forward-looking. I want to focus on industry. We've talked a lot about, there's a lot of focus on strengthening and expanding the industrial base in our country, onshoring, and taking to the next generation what manufacturing and industry looks like in the U.S. What are you most excited about? What are some really bold visionary ideas that we'll see or that you hope we'll see in U.S. industry 20, 30 years from now? Because we know the timelines can be long.
You're the manufacturing guy.
Thank you.
So, here, one more. On the manufacturing side, and I'll go back to what I mentioned earlier, is this is the work they're doing in big metal. So how do you onshore energy technologies that right now we can't make? But part of that too, and something that's very exciting to be going on more on the powder bed scale, is starting to make parts that when you're done with it, you know everything about it. It is born qualified. So an example is we have some brackets that we built during the Browns Ferry nuclear plant in Tennessee. And it's a combination of AI, data, real-time analysis, so that every step we know what's going on. And they've been in Browns Ferry since 2021. We also qualified them through conventional techniques. We'll start pulling them out this year and looking at radiation damage, seeing if they did what we intended. And now we're adapting this technology to make things that ultimately are going to be, 100,000-pound reactor vessels. That's our sort of moonshot goal. So I think if you look 10, 20 years, hopefully not even that long from now, we'll be able to do these things domestically. And I think that would change everything. So I'm an optimist on these things, but it is really cool technology to see.
Yeah, I think what I would add is early in my career, I spent a few years working at General Motors in Flint, Michigan, walking manufacturing plants. And, energy is huge for them. And so I think if we can get cheap, abundant energy for our manufacturing, that's like job number one. But it also then comes down to, their buildings as well, and we're going to have to show them what they used to say in when I would walk the manufacturing plants, when I talk about the energy use, they'd say, I can pay more for energy, or I can pay more to build the capital and sell more product, and I'll make more money. So, energy has to get to the point where it's cheap. And then the other big thing in manufacturing, you were touching on it, both of you, is the digital twins and robotics. And with AI, some of the stuff coming out on the robotics front in terms of, doing human functions is going to be amazing over the next decade, I think. And I think all of that's going to be built into manufacturing. But as every newspaper says right now, it all depends on how much energy we can deliver cheaply and abundantly.
Yeah, we had somebody tour, this was just last week, and I thought they would be really interested in the manufacturing. That was just part of the tour. And they were sort of like, yeah, that's all fine and dandy. Tell us about those robotics. They wanted to know more about that.
Yeah.
Yeah, well, it is fascinating if we look at from discovery science to material science to manufacturing. We are getting better using automated robotics and things like that to do the materials discovery and then to prototype the manufacturing. And we're using AI in both of those, but then into the manufacturing plant, there's been a lot of work at the labs on manufacturing of energy storage technologies here in the United States, because a lot of the storage that we purchase in the United States is not made in the United States. So we need to bring some of that to the United States, but we actually don't have the technicians in the manufacturing plants themselves. We don't have that skill set.
There's a big workforce challenge.
There's a big workforce challenge, and so we need to recreate a competitive landscape that is a core technology for energy systems. And that's going to require a lot of training and a lot of investment in this new workforce that doesn't have that capabilities. The other thing is, we chatted the other day, Carolyn, about traceability. And what's remarkable, if we think about critical materials and supply chain, is where are we getting our critical materials? And now we have tariffs and things like that. We need to understand the global landscape, which is continuously evolving. So when we think about manufacturing, we also think about where are we going to get the materials? How can we more efficiently get mining tailings and things like that and recycling. So recycling of energy storage is such a fascinating topic that all the labs are thinking about. How to actually have this circular economy concept, because there's a lot of valuable materials in kind of the waste products from our manufacturing activities. So it's really a time where we need to look broadly across it and have partnerships with the folks in the room and with DOE and the labs, because these are big challenging problems.
And Marianne, that's a great follow-up question. After the pandemic, everyone became experts in supply chains or even learned that word, right? And now a lot of the country is also aware of critical materials and the challenges on that. I don't know if people are really aware of the substantial work you each do related to supply chains and materials. So maybe each sharing, something you're really excited about that could be really promising to help make U.S. supply chains more resilient.
Well, yeah, maybe I'll start. I will use energy storage, but there's a couple others as well, some that kind of impact buildings as well. Energy storage, Department of Energy has done a phenomenal job really of mapping out the world's energy storage supply chain through all the different parts of the Department of Energy. And as you said, I think 80% of all our batteries, the stuff that's in your phone and on our computers, comes from Asia right now. And a large percentage of that comes from China. And then, the nickel and magnesium, cobalt come from Africa and Malaysia. So we know what the supply chain is, and it's very hard to change a supply chain overnight because we all like everything cheap. So I think there's a very thoughtful and systematic approach of how can we look at recycling. And if EVs and other batteries get up to kind of the scale people predict, then you'll have a big enough market to kind of recycle maybe 20% of the EV usage in the United States. But the real focus has been on the research side is how do you replace those energy storage materials that require a supply chain around the world, like nickel and magnesium. So many of us are working on what's those batteries that will perform at the same level but don't rely on that supply chain that's going to be really hard to change over the short term. And there's good progress going on too on things that are batteries that have less nickel in them, less cobalt in them. They're getting there.
I want to make two comments. There, in Southern California, there's a lithium resource from some brines out in the Salton Sea, and we're working on geothermal energy that also has lithium recovery. So we're trying to create domestic sources of lithium that also have this tie with geothermal. And then adding to what Judd said, we're part of something called the Sodium Ion Consortium. So we're looking for abundant materials, as Judd was alluding to, not just critical materials. So where can we use these other materials in our energy storage technologies? And these sodium ions have been promising, and there's a lot of emphasis on something like that.
Okay, I'll add a couple of specific, these are all great, especially the recycle one. I mean, that's going to be really important. Trying to reduce dependence, so there's a lot of work going on coal to graphite. So Tesla battery, I think that's like 200 pounds of graphite, 60% comes from overseas. Really good progress in that. Coal to carbon fiber precursors. Carbon fiber is a really big deal for all of us. There's other work going on getting rid of permanent magnets in electric motors. And I know people have been working on this for a long time. I think this latest technology you'll see in vehicles. You see it in vehicles, eventually you're going to see it in building appliances. 50% of the electricity used in the U.S. is in electric motors. So you can imagine how much that is, how much material you need for that. So those are just three examples on top of the great examples they had.
One more, because it's one of the coolest things I've seen our scientists develop in my career, and it's if you think about how to make a rod or a tube, you take an ingot of metal and you heat it up and then you push it through a die. It comes out the back of the die, and you spend a lot of energy heating it up. Some of our scientists about 15 years ago said, we have a crazy idea. What, instead of heating this thing up and using all the energy, what if we spun the die? And so the ingot comes and it hits the die and it's spinning and it creates friction and it doesn't fully melt it, but it allows it to, at the atomic level, everything diffuses and you get out, a rod or a tube at the back end. And we made the first of the kind machine in the world. And, it didn't work at first, and then we worked on it and we worked on it. And now it's to the point where you can take things like scrap aluminum and just press it into a little ingot, doesn't have to be fully dense, push it through this device, and out the back end comes a rod or a tube that's fully dense and has some really unique properties in terms of strength and corrosion resistance. So we're getting interest from all different kinds of sectors on how could we use scrap metals and not have to rely on metal processing overseas. And one of the interesting ones was a company came and said, what if we use this for building stock? For metal frames within buildings, we could take scrap aluminum, use your machines, and get a cheaper domestic source of building stock. And so we're exploring that. Our biggest challenge is a U.S. Equipment manufacturer. So it goes back to the supply chain of who makes these big pieces of equipment. They tend to be in Asia or in Europe. So we got to build the equipment
Yeah.
supply chain as well.
That's a great example, though, because I think there's a lot of technologies sitting there that they're sort of waiting for their time, for the rest of technology to catch up, and I think that's a perfect one, because when you guys first did it, it was probably really expensive, really hard.
Yep.
All the supporting technologies have matured. Now there's a pull, and so I mean, there's a lot of things out there that I think are going to show themselves we didn't know existed.
Yeah.
So speaking of limitations, we have some challenges with housing in our country. And so there was a question around multifamily. What do you see as some of the most exciting, promising technologies to really have the next generation of multifamily housing in our country? In an affordable way, but also efficient. Marianne is our...
Yeah, so I think a couple of things. So multifamily housing, because a lot of it is cookie cutter, like the shapes of the buildings, there's a lot of opportunities for prefab, kind of manufactured construction. We're also working on kind of water heating systems that are grid interactive for multifamily, because there's a lot of heat pump water heaters being used in that sector. We're also working on kind of kitchen air quality and making sure that their hoods are working and things like that, so there's healthy places. So we want to make sure that they have quality environments that are affordable. Affordable housing is such a priority for many regions, if not the entire country, and it's critical that we, again, collect the data on how much does it cost, how to reduce those soft costs, and creating kind of the ability to take some of those technologies to scale.
Yeah, you know, I think, especially if I think about kind of low-income multifamily buildings, I saw this fascinating study in the Southeast on an advisory board I was on, where they were looking at where their energy use would be 20 years from now, and it was the parts of the city and the parts of the region that were the low cost, low income housing that didn't have internet, didn't have building management systems, maybe didn't have any kind of controls, didn't have weatherization. And they really made a strong and compelling argument from a big enough picture view of how much transmission they could avoid or new generation build if they were just able to get a low cost, this is a retrofit, a low cost retrofit solution to go into these homes, and they would have to be they'd have to be automated and self-controlling so they could reduce energy use. And the savings was tremendous. But I mean, if I could wave a magic wand, I wish we could figure out how to do that. Go into any low-income building and cheaply and effectively figure out how to help manage the energy costs. It'd make it better for the tenants. You could put new technology on. It would help the whole grid system. But again, it's in the interface of the whole system of how electricity flows, and we need to connect it together a little bit better.
And I would just add or emphasize the affordable retrofit of these homes, and also something that the team's been working on is how do you retrofit them or basically reskin them without people having to move out. And so if you can do all that affordably, I mean, you have a lot of built stock that is not so energy efficient just in the envelope. So combine everything that's been said, and it's a lot.
Can I add something? We've been communicating with folks in Los Angeles County and SoCal Edison around the Altadena fire rebuild. And there are some low-income houses there as well as high-income, but the Pacific Palisades is more a high-income area. So we've been exploring the intersection between fire resilience and energy efficiency. And we know something about the kinds of windows. You know, you don't want a vinyl window in those climates that are high fire danger. You may have more cement. You may have different kinds of air exhaust systems. And so we're trying to understand the building codes as well as the utility incentives. Are there things that we can do to reduce insurance costs? Because insurance is part of the affordability challenge, and we're starting to look at the relationship between energy efficiency, grid interactive, and fire resilience, because that's kind of the future of some of these new designs.
Thanks. So unfortunately, we're getting near the end of our panel, so we're going to do a lightning round. 3 questions that I want to come back to. One is the major barriers or likely promise of nuclear, either as a power source or as a thermal heat source. There was another question about generally around thermal storage. And then one about how we're thinking about the envelope and exciting innovations with building envelopes. So if you could each just pick one, share your reflections quickly.
You guys are looking at me like I'm nuclear.
Actually, I'm thinking nuclear
Are
too, but
you are
You
nuclear?
guys can do new.
but I'll just keep going back to the big metal. Fuel's going to be an issue, but that's a different topic. But how do you make all these things domestically? I'll leave that one at that. But basically, I'll go back to some of the slides I showed on building envelope and being able to automate that, make it more affordable, less just hands-on work to get it done. And it's going to be huge. I mean, all of our areas we live, I'm sure it's like this cross country. Everything's exploding with growth, and but the costs are also out through the roof. I don't know how most people survive, to be honest. It's really out of control. So I'll stop there.
I really hope we get nuclear. We need the firming power. We do a lot of nuclear work. We work with a lot of companies. It still has the challenge of it has to compete the levelized cost of electricity at the end of the day. And so whether, that we haven't deployed a small modular reactor yet in the country. There's one being built in Canada. There's a whole nother generation of advanced reactors that need a fuel supply. I think even if you wanted them to build today, it's still going to take 5, 6, 7, 8, 9, 10 years to get them in place. And then they still have to outcompete natural gas and renewables. But we have to, for them to be successful, I think we have to value the resiliency that they bring to the grid and the reliability that they bring to the grid. So I hope it happens, and I hope it moves quick.
I'll make a quick comment about thermal storage. We're all 3 labs here, plus several others, working on something called Store for Build for buildings. And thermal energy storage has very different properties than electrochemical storage. It can be much more energy efficient, the round trip efficiency of the heat or cooling that you put in and that you get out. And imagine a resilient building that has both, and Judd showed his building had both. So if there are grid outages or even arbitrage and time of use, that energy storage with a battery can actually be a very valuable thing. So thermal storage will continue to have very unique capabilities that is very energy efficient, both heat storage and cool storage in a variety of applications throughout the country.
Awesome.
Can I-
Okay.
One little thing on that.
Yes.
All right, sorry. But on
eyebrows
storage,
you gave.
Carrier recently announced, I don't know if the product's out there, where they're putting batteries basically in their heat pumps. And I think that's really interesting. Think about all your appliances eventually, when it becomes affordable, that is, having
Right.
batteries that can help sort of take the edge off. of
Exactly,
things.
distributed storage,
Yeah.
In your refrigerator. And,
Okay, so last question. What's something that you think is going to transform the lives of the next generation that most people in this room don't know about, aren't thinking about right now?
I'm not going first on that one.
First I'd say, I don't know. Because 30 years ago, me and Judd were talking about this, a generation ago, when we were in school, or I was in school, had no email, no internet, computers were slow, no GPS, no cell phones. And trying to imagine what's next is hard. I'm going to be very optimistic, and maybe it's 2 generations, but quantum's going to be huge to our everyday lives. It's hard to even imagine that, but 60 years ago, it's hard to believe that normal computing would be what it is today. So I'll put my stake on that.
Well, I think I said it earlier. For me, it's with the hyperscalers and everything else we're going to be able to feed information in, it's going to transform how fast we are able to learn new things. And I really agree with some of the high-level things, and I'm trying myself, is either get on board or get left behind, because it is fundamentally going to change how fast people learn, solve problems, come up with new solutions.
So we all know the saying, turning data into information. And so while we can imagine these AI tools, the folks in the room are the ones that are going to help say, what is the information we're actually looking for? What's the value proposition? So I think we need all of you to continue to collaborate with the labs and with DOE on how could we do this together? And I think that we know traceability or the affordable energy technologies. Imagine this ecosystem where there's a lot of information that is available to you. You still have to make choices, and you have to decide what to invest in. So we need investment grade information that helps us do the kinds of things the folks in this room are trying to do.
That's wonderful. So to close out, the answer's in this room and with all of you. So thank you for your partnership. Please join me in appreciating our panel.
Thank you, guys. That was amazing. I really appreciate it. That was terrific. Scary, a little scary, but terrific. Okay, we're almost done with today's plenary. So I want to do a bunch of thank yous. I want to thank the panel again. I want to thank all of you for being here. And I also want to thank all of you for that heartfelt appreciation this morning. I'm glad I had time to recover at my desk. At my desk, that's where my head is, at the table. But, you know, Better Buildings and Better Plants is a total team effort. It's not, Maria. It is a whole team. And I would be remiss and very sad if I didn't take this opportunity and ask for your help in thanking the Better Buildings team who made this summit and all the work we do with you throughout the year possible. So if you're a member of the Better Buildings team, whether you're a lab, account manager, whether in any way you help in Better Buildings, will you guys please stand and we can say thank you as a group to all of you. So. Thank you for you doing that with me. And just one more group I want to thank. Doing this summit every year is a huge lift. And so there are a couple people that focus for, believe it or not, about 9 to 10 months to get this all together and get it here and get the sessions organized and do everything possible to make sure you have a great experience. Marissa Schatz was our fearless leader. You can't miss her. She's in a pink blazer. Marissa worked with Julia and Brooke and Mike and Emily and Lindsay. So if you guys will just stand up, I would really appreciate it. It's a huge team effort. So. Terrific. Okay, so now we're just going to talk about what's ahead of us today. So we are on time. It is 10:30, and at 10:30 till 11, there is the Ask an Expert session in the Capitol Terrace. And so, again, I was asking folks if people take advantage of the Ask an Expert yesterday, and apparently a lot of people did. So here's your chance to do that yet again. Talk to experts many of them from the national labs on specific technologies and other things that we work with partners on. So please take advantage of that. There are sessions at both 11 and 1. They're just 1-hour sessions. We made the second day of the summit short, so we're hoping that you stay till the end of the summit. So there will be a session at 1 that'll last an hour, and then there's lunch and a session at 1. I want to thank you all again for being here. Please, I know this is like the 18th time you've heard this, but please do give us some feedback on the summit and then Better Buildings moving forward. And with that, I thank all of you for being partners, for working with us, and for being here today. So thank you. Enjoy the rest of the summit and safe travels home. Thank you.